So just a quick recap of the rest of our week then. Today we're going to talk about gravity projectiles. Tomorrow is a work day. Finish up your lab. Finish up some of the assignments if you can. And then Thursday's our quiz. We don't have school Friday. I should double check. You guys don't have school Friday either, right?
No.
Okay, good. That would be interesting. Okay, so no school Friday, so we have a nice long weekend. Yay. And then Monday by the end of the day, finish your labs, okay? So I don't need them by the first class of the day, but before I leave on Monday, make sure I get them, because I want to get them marked and over with as soon as possible. Okay, let's talk about our notes here. What we focused on so far really is linear motion. Linear meaning like straight line, one dimension. If we were to plot a graph of what we did yesterday with the Hot Wheels cars, really if this is your Hot Wheels track, the Hot Wheels cars went in a perfectly one-dimensional straight line. Which makes sense, that's what we're starting, real easy. But that's not the only kind of motion we can have, right? We're often going to have motion in multiple dimensions. The x direction, like flat. But we also need to account for what happens if it's also going in, say, the up and down, y direction. We only cover x and y in this course. But it is possible to have, like, x, tip it up a little bit for y, and then you could even rotate it on the z-axis, if that makes sense. We won't do the z-axis, we'll just do x and y. And so that's our goal now, is to start talking about, well, what happens if the motion is not a linear motion? And for those of you who've taken Math 20 all the way through, you'll recognize this part of a graph here. This straight line graph is considered a linear graph, but gravity doesn't act in a linear motion. If I were to shoot a cannonball off the cliff, it does not go in a straight line like this, right? It goes like this, and so it has a motion called a parabolic motion. You guys recognize the term parabola from last year? You guys in my grade 11 class, we are going to get to this at some point. But it's got kind of a curved section to it. So we need to start talking about not just the x direction, but the like the x and y direction. So first definition here, a projectile then is basically an object who is in motion and gravity affects it. It's been released, however, so there's no longer any other forces on it except for gravity. So I throw this thing. Once I've finished my throwing motion and it's in the air, it's considered a projectile, because really all that's affecting it is gravity. If gravity did not affect my throw of the ruler, it would have just kept going in a straight line for forever. Anybody ever watch really any outer space movie? Like I'm thinking of like the one called Gravity, or say The Martian or something like that, where they're in outer space, right? And there is no gravity. Once you're in motion, when there's no gravity, you're going on a straight line for forever. You know what I'm talking about here? Where like in some of those movies, they're really worried about maybe not making their landing or something like that, or they go outside of their spaceship and their cord gets cut and they start moving this way. And once they start moving this way, you really can't go back the other way. You guys know what I'm talking about here? Because of gravity, gravity will pull us back down to Earth. Otherwise, you just go in a straight line for forever. So here's some example pictures then. You could just drop something straight down, and as it gets dropped straight down, it's going to keep speeding up, right? Acceleration is pulling it down faster and faster and faster. I could throw something straight up in the air, just straight up in the air. And so that's what this is supposed to represent. As I throw it up in the air, if it wasn't for gravity, it would just keep going up and up and up for forever, right? Kind of like the spaceship concept on like The Martian, where if they bounce off the surface of Mars too hard and they get too far up, gravity won't pull them back down again, and they'll just be lost in outer space. But due to gravity, you know, it's going to go up, but it will come back down again. Or what we could have is this nice parabola shape as well, where I don't just throw it straight up. I throw it straight up at a bit of an angle, and it has a nice little arc to it. So, a little bit of history. Not that I'm going to test you on this really, but I'd like you to know some of these famous scientists of the past. Aristotle, maybe a name that you've heard of before. He had this idea that objects fell with a constant velocity, and it was proportional to mass. Aristotle actually wasn't completely wrong. Some objects do eventually fall with the same velocity. I've got slides on it coming up later, but it's called the terminal velocity. Once it reaches a certain speed, things don't speed up anymore because air resistance will actually even out how much gravity is causing the speed up, and at some point you just can't fall any faster. You guys ever talked about this before? The idea being that like gravity is trying to pull you down faster and faster and faster, but at some point the air resistance is actually going to push you back up, and so you're still going to go down, right? But you won't speed up any further. Yeah. So Aristotle was kind of right, but he was incorrect on this one here. It wasn't really proportional to mass. Okay. Do heavier things fall faster? No. Right? Think of all the formulas we would be using here. Does mass actually make a difference? Alright, let's do a quick demo. What can I drop here? There's two different sized objects. Different masses, right? 3, 2, 1. Same time, right? So, is that true? Yeah, mass should be irrelevant based on how fast they fall. They're going to hit the ground at the same time, right? Now, with how much force they hit with, I'm okay with a pen hitting my foot. A bowling ball hitting my foot will probably break bones, though, right? So there is a difference between how fast they fall and how much force they hit with. So Aristotle wasn't correct about the proportional mass sort of thing, but he was kind of right about the constant velocity. Everything will hit a terminal velocity at some point. Okay, then Galileo has another idea. He kind of improves on the concept and determines that they're supposed to accelerate uniformly, and he figured out that the acceleration is independent of mass. The next kind of line here, so mass does not really matter. He figured out basically that gravity pulls everything at the same speed. No, gravity pulls everything at the same acceleration, closer and closer to the Earth's surface. So we've always kind of told you guys that gravity is 9.81 meters per second. It's not. That's just our closest approximation. Most of the time, it's something closer to this, but it actually depends on where on Earth you are. If you are like up high on like a mountaintop, gravity actually has less effect the further off the Earth's surface you are. So if you're on Mount Everest, gravity is more like 9.6. As you come like closer and closer back down to Earth, it actually becomes 9.7, 9.8. But it depends on your location to sea level. Most of the time, though, we're just going to go with the 9.81 value. That should work. Here's one of the issues, though. This does limit us on sig digs. So whenever we use 9.81, I guarantee you cannot have more than 3 sig digs. Let's do an example. You drop a large steel ball from a height of 7 meters. How fast will it hit the floor? Does it matter that it was a large steel ball versus a pen? Does mass matter? On this one here, it actually seems like we don't have a lot of information. It seems like I gave you one number and that's it. That's actually not true. We've got actually a few other numbers that we can work with. So, although this thing is going to travel a distance of 7 meters, we know what the acceleration due to gravity is going to be. It's 9.81, right? Meters per second squared. Here's where we have to make a decision. We have to decide whether down is going to be negative or whether down is going to be positive. It doesn't matter, but we have to be consistent. So what I could do is I could say that the distance I'm traveling is going down 7 meters, which would mean the acceleration is also going down. I could have chosen the distance to be going down, being like, I'll make down be the positive direction, but then it also means that the acceleration has to be positive. What we can't do is do one of each, though. Does that make sense? So you have to be consistent. Either down is considered negative in our minds, or down is considered positive in our minds, whichever one you want to go with. So I think just to keep it simple, let's go with positive for both of these. What's the hidden number? What's the number that we don't know about, or that we do have a value for, but it doesn't say? Well, that's what we're looking for. We're looking for velocity final. I need one more, which is? Good. Yeah. Our initial velocity is 0 because the steel ball was dropped. Okay, well, this is just one of your basic formulas, right? So we need d, no, we don't need that one. We need vf squared equals vi squared plus 2ad. At this point here, I just need you guys to do basic algebra, right? Let me know when he gets an answer. .7. Sig digs. I get 3, right? I need to be more specific here, though. This was a velocity. So although we chose for positive to be in the downward direction, because we got a positive number, we should make note that this is going down. Obviously, right? Things falling in the downward direction. Hypothetically, let's say that this was 7.000 meters. Let's say we had an extra sig dig. We would only get 3 though, right? Because gravity is going to limit us to the 3 sig digs we get from it. Any issues on the first one? Nice. All right. Amusement park ride. At the crest of a rise begins a vertical free fall. So what I'm going for in this picture, if you can imagine it, you're doing like a roller coaster. You're coming up the top. You know, this is the car on the roller coaster here. Right, here's you in the roller coaster with your hands in the air. Really big hands in the air, apparently. Yay! All right, you're about to hit the crest of the fall, and then like you're going straight off a cliff kind of thing, right? So I'm asking you 2 things now. I want the distance traveled and the velocity you reach after 1.5 seconds. So again, I only give you one number, right? But there's hidden information we need to make sure we're aware of. So although sure, we have a time of 1.5 seconds, we still know an acceleration, right? Because gravity is 9.81 meters per second squared. And again, like with the last one here, we're hitting a vertical free fall where like you barely, the goal I was having on this one here is where you just barely, nudge over the top and kind of fall down. So the last thing we know is that our velocity initial, basically you have no initial velocity, right? You're starting on a free fall. So we got to do this twice. We got to find a distance and we have to find an acceleration. Let's ignore the acceleration one for the time being. What formula involves distance, velocity, initial, acceleration, time? Sorry, this is the velocity final. My bad. Okay, so if we want to use these 4 variables, we need what? D equals VIT plus 1/2 AT squared. That'll work. Okay, we don't know how far we're falling. We know that we started with no speed. And we have to times by time, which although it was 1.5 seconds, honestly, that's really, it's gone, right? We don't need any of that. Then we need 1/2 of our acceleration. Let's talk about our negative sign real quick here. Let's say we wanted to make it negative 9.81 meters per second. What would it give us for a distance? It would give us a negative distance, right? Well, it just means that since we were accelerating in a negative direction, our distance is also going to be in a negative direction. So, I mean, if you want to go with negatives, you can. I think, again, in this case here, it's probably just simpler to stick with positive 9.81 though. And you do that for 1.5 seconds. You have an answer? What did you get? 11 with 2 sig digs?
Yeah.
Cool. Okay. Well, we now know the distance was 11 meters. And we want to try to find that final velocity. Okay, let me give you some advice here. Although we could use any formula now, right? We could use a formula that involves velocity final, velocity initial, acceleration, and distance. I could, for example, use velocity final squared equals velocity initial squared plus 2AD. That one would work. The advice I would give is, since this was a calculated value of 11 meters, you don't want to actually put the 11 into the formula, because that number was actually 11 point blah, blah, blah. You know what I mean there? So I probably would not choose to use this formula just because I know that this number here was a calculated value, and that little bit of rounding could cause an issue, even if I use the whole number. So I think it may be preferable to try to find a formula that has velocity final, velocity initial, acceleration, and time, and not use the distance we just calculated, if we can avoid it. If you cannot avoid it, though, do not put the number 11 in there. Make sure you use the number 11 point whatever you got, right? Make sure you use the exact value. That being said, I'm going to try using a formula that involves velocity final, velocity initial, acceleration, and time. That's going to be like your acceleration is equal to change in velocity over change in time. This one looks like it only has 3 variables in it. But I've shown you this before. We can kind of write it a bit differently. We can write it as your velocity final minus your velocity initial over your time. We talked about how this one actually has, like, hidden in this change in velocity, it's really your final minus your initial. So our acceleration was 9.81 meters per second squared. Velocity final is what we're looking for. Our initial velocity was 0, so I'm not even going to bother writing it. And our time was 1.5. Shoot that guy up there. We'll get your velocity final. It's got to be what, like 14 point something? Enough to round up to 15 or just 14? 15 meters per second. You guys get why I suggested to use this formula rather than this one up here? It's one less chance of making a mistake, because if we calculated our distance incorrectly, or we rounded it wrong or something like that, if we can avoid that, that's a good idea. That being said, it still should work, right? So I mean, if you wanted to, you could do your velocity initial squared, so basically ignore that number there. Take 2 times by 9.81 times by your exact distance of 11 point whatever it was, square root it. Should give you the same thing. Right? I'm trying to find ways to prevent mistakes. So far, so good. Okay. So here I've got some slides on some stuff I've mentioned before, just off the cuff, but I want to make sure I've covered this thoroughly. There is a terminal velocity for pretty much every object. This piece of paper here hit its terminal velocity very quickly. Is gravity going to try to pull it down? Absolutely. But due to the flat nature of that piece of paper, air resistance is going to start pushing back up on it. Okay? It's still going to have a velocity going down, but it's not speeding up faster and faster and faster. And so when, like, for example, when someone goes skydiving, which I think is on my next slide, maybe. Yeah, here's a picture of a skydiver. Gravity, his weight is pulling him backwards, but drag is trying to, like, pull him back up a little ways. So long as gravity outweighs the drag for a while, then he'll keep accelerating faster and faster downwards, right? When he eventually pulls his parachute and the parachute comes out and that, has a lot of drag on it, eventually the amount of drag basically is exactly the same as his weight. And it's actually going to start slowing him down perhaps even, because there's going to be more drag than there is weight. Does that concept make sense? So every object is going to have a different drag coefficient. So I found this picture online. I would never expect you to try to calculate this stuff. But I mean, if you were a sphere, you have a reasonable amount of drag. If you are like streamlined, you know how they try to make like race cars and missiles fairly aerodynamic, right? It's going to cut down on the amount of friction you have. So if I were to make a car that was a box like this, you can see the drag coefficient, not all that good, right? But if I make that same shape, but I like kind of cut out the edges and try to make it more like a teardrop, streamlined, there's way less friction slowing it down. Makes sense. When I think of this, I think of you know how you do like boxcar races where you get like a chunk of wood and then you put wheels on it and it has to just roll down the ramp, and all that you have is gravity, right? Right. Well, the person who makes the big clunky sphere isn't as aerodynamic as this one here. But you know why you really win those races? It's not the friction to drag, it's the friction on the tires. That's what actually slows you down on those sorts of things. So you could build a boxcar thing, just that's a cube, and if you had just the best tires in the world that had no friction, you'd probably win. That actually makes a difference. Anyways, terminal velocity, I kind of got off topic there. At some point, the drag coefficient pulling you back up is going to be the same as the gravity pulling you back down, and you just won't go any faster. You'll just hit your final speed. So, however, we are typically going to ignore air resistance. So, when we did our lab yesterday, was there air resistance on the cars that went down the track? Yeah. And so maybe two different cars had different drag coefficients due to that. When we eventually do a lab in a week and a half where we shoot some Nerf darts through the air, we'll actually be able to see the effects of air resistance on them, especially if we go outside and it's windy, because that just adds to the variables. All right. I found this slide on a NASA website somewhere. It's possible to calculate these sorts of things. We're not doing this, by the way. Please don't be intimidated and go, holy smokes, where did this come from? But they can actually calculate terminal velocities, but you'd actually have to know things like your actual velocity, your gas density, because it depends on what you're traveling through, right? Think of it as like when you are trying to swim. When you're trying to swim, you have to manipulate your body through water, and the water is slowing you down, right? Does air really slow you down when you try to walk through it? Well, not really. If it was really windy out and it was blowing right into your face, then maybe it would, right? So that's why gas density matters, because it depends on how thick the atmosphere happens to be at that point as to how much resistance there would be. You'd also have to know how much frontal area the, like for example, this right here has a very, very small amount of area on the front of it, right? Because it's been streamlined. If this missile right here had like a box on the front of it, there's more area. You also have to know how to calculate a drag coefficient, which apparently, anyways, we're not doing this. But you guys get the concept though that you could if you had the right, training on this. Okay, I've got two last questions here. But this one here has a twist. Everything we've talked about so far, I've just dropped. What if you're not dropping it? What if I won't throw it, but what if I throw it up and then gravity brings it down? Or what if I just throw it directly downwards? Okay? So what happens if it's not just a drop, but it actually has some initial velocity to it? So that's our last twist. So let's start writing out what we know. We're throwing a ball with an initial velocity of 12 meters per second. Time is 3.45 seconds. What else do I know? I know acceleration, right? Okay, we should talk about this here, though. Should we need any negative or positive signs here? Our velocity initial, we were throwing something down. Which way is acceleration going to pull it? Also down. That's where the big difference is going to be. If I throw something down, my velocity and my acceleration must have the same units. If I threw something up, and then it eventually goes down to the gravity, I would have to make these signs be the opposites of each other.
So that would change.
So long as you're consistent. So you have to decide whether down is negative in your mind or whether down is positive in your mind. Well, you just have to figure out your perspective. But that's the point I want to make here, is that since they were both going down, they both require the same sign. If gravity pulls it down and you threw it up, one of them has to be a different sign. Okay, so our question is going to be first, how fast is the ball traveling after 3.45 seconds? So we need to find the final velocity. What formula do I use? It's the one that's really sneaky. It doesn't look like it has 4 variables, but it's that your acceleration is your change in velocity over your time, however they write that on the formula sheet. Because it's really velocity final minus velocity initial over time. That one's sneaky. It doesn't look like it has 4 variables, but it does. Alright, so our acceleration, 9.81 meters per second squared. My velocity final is what we're looking for. Our velocity initial was 12. And our time was the 3.45. Algebraically, how do you get velocity final by itself? What do you have to do first? Yeah, you have to multiply the 345 first, and then add 12. Swing that guy up there, times those together. I'll just write it out like this, 9.81 meters per second squared times the 3.45 seconds. And then you'll have to add 12 to both sides to get your final velocity. Which kind of makes sense, because wasn't this thing already moving when we threw it downwards? Because it was already moving as I threw it downwards, we need to add some extra velocity on, and that wouldn't be there if you just dropped it, right? Anybody get an answer? 46? Okay, as I look at the follow-up questions, I realize that they don't really make much sense. Because it says, what is the ball at the maximum height? And what is this maximum height? Isn't the maximum height going to be wherever it is you threw it down from? Yeah. So I think I made one slight typo here, but this is actually a really good learning moment. I think I really intended for this word to be up, because that would have made way more sense for me to teach you a bunch of things. Because now let's talk about how that changes the scenario. If I throw this up in the air, I won't throw my big pen off, throw this one here. So here's where I'm throwing it from, right? As I throw it up in the air, its maximum height is somewhere higher than me. Does that make sense? Right. And we could also try to figure out how high that is and when it reached that point. So let's talk through this question here again and see what would have changed differently if I'd have actually thrown it up. What's the one thing I would need to change in all the math we just did if it was up, not down? Yeah, I just have to flip the positives and negatives, right? So we should make sure we're clear, though, as to which direction is going to be which. So why don't we make up be, let's go up be positive, and let's make down be negative. We just need to make sure we're clear on that. So then the only difference now would be that acceleration would actually be a negative number. Well, it doesn't change a lot of our math, right? It just means this is a negative number. It means that's a negative number. So sorry that I'm making you change all this, but I think we're going to learn something from my typo. What would the velocity final have been in this case here? So negative 9.81 times the 3.54 plus the 12. Is it the same value? Because it used to be like roughly, that's roughly about what, 30 plus 12 more for 40 something?
21.8.
Thank you. 21.8. So negative 22 then? Why is it negative?
Yeah.
Do you see why you can't just assign a negative? You actually have to redo the calculation. Why is your final answer negative though this time? I threw the thing up in the air. I gave it a positive velocity to begin with, right? What's happened after 3.45 seconds? It's not going down, because it's already begun its descent, right? It's gone up in the air and it's now on its downward section, right? So that's why it's negative, because it's actually starting to come back downwards. Okay, so now let's answer these follow-up questions. And maybe to do that, it'll help to draw a bit of a picture then of what we have happening. I stood right about here, on the edge of, say, a cliff. I threw it up in the air, and it's, make this sort of motion to it. When this thing is at its maximum height right here, what's its velocity going to be?
0.
Yeah, for that brief moment in time. I mean, granted, I'm throwing it like this, but let's just throw it straight up. For that brief moment in time as it hovers up in the air, isn't it going to have a velocity that basically has stopped for a second? So that's what we can actually use to help us solve this issue here, is we actually know our initial velocity. Our final velocity, for a brief moment in time, at least in the up and down direction, it's not moving anymore. We know the acceleration is negative 9.81 meters per second because it's pulling us down. Let's solve for time. So we can actually figure out when it will be at its highest point, because we know that at its highest point, it briefly stops. Again, don't look at the diagram like I'm throwing it forward. Think of it more as though I'm throwing it straight up in the air and back down again. Right? Like basketball players, when they dunk, they appear to kind of hover for a second, because really as they go up, as they're at the top of their peak, they do really, in essence, kind of pause and stall before they come back down. They're just able to kind of make it seem like they're exaggerating it, but it does, right there, no velocity. Okay, so to solve this one then, what do we need? We need that same formula, don't we? Acceleration equals your velocity final minus your velocity initial over your time. Our acceleration is pulling us downwards. Is that what we said we wanted to do? Yeah, negative. No velocity final though. Velocity initial was 12. So I want to make sure we're really clear about the signs here. It's supposed to be velocity final minus velocity initial, but the velocity initial is going up, so we need to minus a positive 12 meters per second. If it was going down, we'd have to subtract a negative. Make sure you're very clear on the plus and minuses, because that will kill you otherwise. And then solve for time. So really, you just need to switch these variables around. Time is going to be equal to negative 12 meters per second divided by negative 9.81 meters per second squared. Isn't it good that both of those numbers are negative?
So how come the 12 is negative?
Okay, because the formula itself calls for a negative sign, but the velocity initial is positive. So what you have is 0 minus the minus b doing to do the formula, and then positive 12. So 0 subtract 12 is still negative, right? Got me on?
Yeah.
So the point I want to make here that is, that's good though, right? Because if both of these numbers are negative, two negatives would cancel and give you a positive, which is good because we solved for time, right? Unless you found a way to open up a wormhole and go backwards in time, right? Like, no, that makes sense. What'd you guys get? Perfect. Okay, and then last thing, let's figure out, what was it? Let's figure out the maximum height. Let's figure out how high this happens to be a distance. Really, that's just the other variable we haven't solved for. So I'm going to try, let's see, velocity final squared equals velocity initial squared plus 2AD. I'll try this one now. As this thing is thrown up into the air, we recognize that for that split second that it's in the air, it's not really going to have a velocity. At least not in the not in the up and down direction, right? If I throw it straight up, it's going to hover for like that moment before falling back down. So there is no velocity final. Our velocity initial is going to be positive 12 meters per second squared. However, our acceleration is going in the opposite direction, negative 9.81 meters per second. That's our distance. How do you solve for this d right here? We gotta get rid of the 2 and the 9.81. But we also gotta get rid of this 12 squared. What was that? Well, if we divide the d out, where's that going to take? Like, if I divide this by d, I'd have to divide this by d, I'd have to divide that by d. I'm not really sure if that's so helpful.
Well, the calculations, add all those together.
Okay, so let's do that. 12 squared is 144. I'll just skip units temporarily. 2 times 9.81 is minus, what's it, 19.62. All right. So now consider it to look at this instead. How do you get d by itself? Yeah, okay, so you have a couple options. What you could do is you could take the 144 to the other side. All right, like you can subtract the 144 to the other side. You could even add this thing to the other side. Divide by 144, divide by 144. We got two negatives dividing by each other again. Should give us a positive. Is that expected? Should this be a positive? We define positive as being up and negative as being down. Should our distance be a positive number? That would make sense, wouldn't it? If we had a distance being a negative number, then that would have gone downwards there.
Could you explain how you got the positive? I don't get, why did you put the 144 over and then divide it again?
Like at this point right here?
Yeah.
Basically, I subtracted 144 from both sides.
Yeah.
So you get negative 144 equals minus. Oh, I screwed that up, didn't I?
Yeah, don't you add that when you divide?
Well, okay, so you got options. I should have divided by 19.62 though, shouldn't I? I screwed that one up when I showed it there. Jimmy, what you could have done at this point here is you could have added the 19.62 to the other side. I screwed up though. I divided by the wrong number though, didn't I? It wasn't the 144 you divide by, it's the 1962 you divide by. I got ahead of myself. The point I wanted to make was that two negatives were canceling to give a positive, which does make logical sense. You guys okay now? My bad. What'd you get? 7.3? Okay, so the big twist that I need you guys to be prepared for in terms of the new stuff we're covering here, you have to get your positives and negatives correct, because it blows the whole thing up if you get them wrong. So the advice I give, if things are going in opposite directions, if something's always just going that way, don't worry about it. But if like a velocity is going this way and an acceleration is going this way and a distance could be that way, just define however it is you want to do it. One way is positive and one way is negative. And make sure you use your common sense when you're done to make sure that, like, if you do get a positive or a negative, then it makes sense. One last thought before I do my last example, because that was actually not nearly as much. Let's say I gave you an example where you had to throw something up in the air, and I was asking for what time it ended up occurring. And let's say over the course of solving this, you had to use the quadratic formula because you used this formula right here. Let's say I gave you the distance that it was traveling. You wanted to know when it was this high above the ground. Let's say I gave you the initial velocity. Let's say you knew what the acceleration was, and you used the quadratic formula. The quadratic formula gives you two answers. Why do we have two answers? Well, because look, this object would have been this high in the air at this point, but it also would have been this high in the air on the way back down again, right? If I ask you as I throw my pen up in the air, where was it 2 meters above the ground? If this is 2 meters, it was 2 meters above the ground on the way up and on the way down. So it actually can make sense, by the way, for you to have two answers in this scenario here, the one where you use the quadratic formula with the t and t squared formula. That makes sense? It also really relates to what we're doing in math right now, right? The whole, how can you have two answers yourself? Okay, last one. You guys ever hear how they talk about something called like G-force, or how many G's something undergoes? If you haven't, it basically, a G is a measure of how much acceleration your body experiences. Maybe you've seen like a photo of astronauts when they prepare to go into outer space and they go through like one of those things that just spins them around in circles like crazy, and you try to see how fast you can accelerate until eventually you probably throw up. You know what I'm talking about, those things there? Right? The human body can really only withstand so many G's before you black out, like your body just can't handle it. Fighter pilots, for example, when they need to accelerate in their F-22s or something like that, they need to be able to handle doing all of their flips and tricks without blacking out, right? So anyways, G's is a force of gravity. Basically what it refers to is how much acceleration you undergo. So if you undergo 1 G, you're undergoing 9.81 for acceleration. If you're undergoing 5 G's, it means that you're going 5 times 9.81 meters per second squared. A G is a measure of how much acceleration you have. So if this ever comes up, 5 G's, that actually is how much acceleration you're undergoing here. How fast were they traveling though? This is a trick question. If I ever refer to something and how much G's it has, that just tells you how much acceleration you're undergoing. We don't actually happen to know how fast you're traveling. You get the difference between the two there? If you talk about how many G's something does, it's not the top speed of a plane or the top speed of an aircraft. It's the top acceleration of the thing there. So the trick question here is that it does not tell you anything about how fast you're traveling. Because really, so long as you keep accelerating at that speed, you'll just keep going faster and faster and faster and faster. Does that make sense? So people don't black out due to G's due to high speed. They black out due to high accelerations. Your brain can't handle the acceleration. I believe there's something to do with the blood vessels and stuff like that, causing you to lose consciousness. That make sense? So summary of the day. Biggest thing I need you to take away from, you got to get your positives and negatives right. If one thing's going one way and one thing's going the other way, pick a direction, label your positives and negatives. Otherwise, most of this really is the same as all the formulas we've been using. Right? So long as you can algebraically manipulate them, it's the same sort of stuff. Questions, comments, concerns, etc. Good? I've been talking for a while. I know we've only got like 20 minutes left. Maybe take a quick break. And then the next day and a half then is work on your lab, work on your assignments. I'll have a key ready as soon as I can.
You said tomorrow or work?
Tomorrow's work day, yeah. But you still have 20 minutes today too. So go take a quick break. I know I need to stretch my legs a bit here.